In addition to you two gentlemen, are there any other people who don't speak Mandarin? Mandarin, okay. I forgot that probably there are some other Asian students who look very like Taiwanese, and I miss them. Okay, that wouldn't be good. All right. So, all right, good. Okay. Look, I will emphasize again the possibility of watching the class, the lectures I gave in Tuesday's course. This time I will give it, I'll say it again in Chinese, in Mandarin. Okay, please forgive me. 礼拜二控制的课也是我教的哈，然后教课的内容跟今天教课的我们的这堂课，我会尽量的让它都平行进度，尽量差不多，不可能完全一样。那内容也不可能完全一样，但大致上都是同样的 PowerPoint 的东西。了不起就是礼拜五做了以后，我发现有些地方我做的不够好，礼拜三上课的时候我会再改一改。然后录影带都会放在 YouTube 上面，然后建议大家，我礼拜二上完课，礼拜二很快学长就上载上去，你可以先看，先预习。那因为都是中文的，希望听起来就觉得说比较有亲和力，然后再听是英文的课，好不好？好。然后呢 ，I hope by previewing everything, previewing the teaching materials of this class by previewing what I taught yesterday, okay, will be helpful. All right. Now, after introducing system identification, signal processing, and system analysis, let's switch our attention to our central goal, which is control. Yes, as you can anticipate, now the system is known. The output has also been specified. Now the question is that how do you determine the input? Okay, so the reason why we want to study control series is that we want to find a good way to help us determine the input so we can get our job done. This is a control example, all right? This is an adaptive cruise control system, which I think this closed feedback system is already available in many vehicles selling today, okay? Cruise control is simply a basic version of adaptive cruise control because it just keeps your car at a set speed, say 100 kilometers per hour. Adaptive cruise control is another thing. It will use sensors such as radar, LiDAR, or cameras to monitor the vehicle ahead of you, okay? So in order to use ACC, you have to manually specify the vehicle or the car you want to follow. And it will automatically adjust your car speed to maintain a safe, constant following distance. So the goal here is, so for control problem, the system is known, of course, your car, okay? And the design output has also been specified. What is that? The distance between your car and the car ahead of you, okay? This is a very good feedback control system because it's made driving in highway much less stressful, okay? You don't need your full attention, okay? You let the computer drive the car for you. Of course, there are some special cases. ACC might dysfunction, okay, or its operation is not clean enough, and then you interfere, okay. But for the most part, it is a wonderful tool, okay. All right. So what is control? Control is the process of causing the output of a system to conform to some desired value. Okay, so you have to set the output first. Okay, how do you do that? By adjusting the input of the system. Okay, now adjusting the input of the systems is not easy, because to do that, you need to know the systems, and you need to know what are the disturbances or uncertainties will be involved. Okay. Now, I want to emphasize two things. In this course, concept is much important than method. Okay. That is, don't expect to come to this course and learn one control methods that you can use all the time in the futures. That is not the case. That is, for example, you go to the fighting club, you tell the coach, tell me how to fight so I can fight every battle. There is no such things. Now, what the coach can teach me is that I can teach you some fighting techniques to protect yourself. But how do you apply those fighting techniques? It really depends. It really depends. Depends on your opponents. Depends on the environment. It depends on the tools you can use. But the concept of defense, the basic concept of good fighting techniques are something I can share with you. Okay, same thing happened to control. All right. Now, another thing I want to emphasize is control is conceptually abstract. Okay, it is very, very. It is not easy to understand. It's relatively concept. It is relatively abstract. It's just not that down to. You just cannot come out with a down to earth description and then say, okay, this is what it is. I got it. All right. It's not what it is. Okay. For myself, as I said, I did my master PhD degree in the control division. Okay. So my master and PhD thesis are about control, in particular, automotive control. But I become, I think, more relatively comfortable with control after 40s. Okay, and when I was 50 years old, I finally really think I know a thing or two about control. Okay, so it really takes some time to grasp the idea of control. All right, so if you learn control and you think, shit, why is it so complex? What does it want to do? Okay, don't be frustrated. It is the materials itself make things difficult. Okay, don't blame yourself. Okay, now let's go to another topic. Okay, classification of control systems. There are many ways, different standards to classify control systems. The most basic classification criterion is open loop versus closed loop. What is an open loop control system? It's like a fan. You turn it on, and there are a few things you can do. You can adjust the speed of the fan. You probably determine whether you want it to rotate its head. Okay, and that's pretty much about it. Okay, so open loop control system is a system in which the output has no effect on the control actions. Once you set the input, it will just go the way it's supposed to go. It will not do any adaptive adjustments. When I say adaptive, I mean adaptive to the output, adapted to the real operation condition. Its behaviors will always be fixed. Okay, feedback control system is what we say closed loop control system. So feedback control, closed loop control, same thing. Okay, and feedback control system is this. Control systems are the systems in which the output arrow is fed to the controller to improve the performance of the system. Okay, so there are two keywords here. One is output error. The second is, of course, feedback. Okay, but to the controller. Okay, so one key concept coming here. That is the control. First, you need a controller. Second, the operation of controller depends entirely. Entirely. It depends only on one thing: error, output error. Okay, it based on decisions based entirely on output error. So the philosophy of feedback control system is entirely error driven. Okay, it's entirely error driven. So the ultimate goal is, by using feedback or closed loop feedback mechanisms, I want to reduce the error as much as possible. Okay, that is one fundamental code. Okay, but there are, of course, other things we need to pay attention to. Let me give you an example to illustrate the difference between open loop and closed loop control. Let's say we have a cannon versus a missile. A traditional cannon is essentially an open loop system. Why? Because it has no feedback. Once you shut the cannon, okay, you cannot do anything about it. Okay, everything is pre-calculated. Okay, that means all targeting operation must be done. I'm very sorry. Okay, I'm so sorry. Must be prepared beforehand. Okay, and forget. Once you start operations, forget about any. You forget everything, because there is nothing you can do. Okay, if you really want to do something about it, you have to do it afterwards. That is, you have to apply for this cannon system. You have to do external correction only. That is, if I miss, I must manually adjust the cannon's positions and fire again. As you can see, this is not very efficient. All right. Now, closed control is like missiles. Okay. First, it is real-time feedback. Keyword here is real-time. Okay. Of course, there will be some time delays between the actual position velocity, between the actual trajectory of the missile and the control command. Okay, there will also be some time delay. But if the real-time control specifications can be met, okay, things will still work. Okay, and the reason why missile is better than cannon is that it has active correction, which means during the process of its entire operation process, the missile will continuously ask, where am I? Where should I be? Okay, will continuously ask these two questions, and based on the answers of these two questions, it will actively correct its moving direction and moving speed. Okay, and in order to do that, okay, to know where am I, where should I be, I need sensors, often multiple sensors, such as GPS, radar, things like that. Okay, and feedback control can have adaptive response. Okay, because you will run into countermeasures. All right, how do you remove or compensate the effects of those countermeasures? And you will also probably run into changing conditions. Weather can be different. Okay, you can run into typhoon, run into very unfavorable weather climates. Okay, now and all those factors can have a strong impact on the flying trajectory of the missile. And it is the duty of the feedback controller to compensate to counteract those unpredictable uncertainties. All right. Now, I want you to get to the goal of the next example is to tell you that control exists not just in any engineering systems. Okay, it exists pretty much everywhere in our life, including healthcare. Let's say I'm a diabetes patient. I have to inject insulin into my body, okay, to control my glucose. So what I do is when we go here in Taiwan, we go to a doctor and doctor say, okay, Vincent, you have a problem, okay? You have a disease. I will give you some prescriptions. Take this medicine 3 times a day after meal. And then I go home. I take those medicines 3 times a day for a week. And during that period, I don't do any medical diagnosis to monitor the change of my body. So it is pretty much open control, right? Okay, you give me prescription, I take medicines. The medicine probably will work, probably will not work. Probably I take medicine, I don't need to take a week's medicine. I probably take 1 day's medicine and I killed, I recovered. But doctor told me I should take the medicine for a week, and I'll just do that, right? Okay, so that's open control. Okay, I'm not saying it's not working, but it's not good enough, right? So for diabetes patient, an open closed-loop feedback control system does exist. For example, there is a thing what we call artificial pancreas. Now here we have desired glucose set points, and here the problem, I think the trouble here is that you need to build a sensor inside your body to measure the glucose of not your body, my body. I'm the patient with diabetes problems, and once my glucose is above a certain levels, then this machine will, which is essentially an insulin pump. So it is a mechanical pump. You will pump the insulin or inject the insulin into my body. Okay, the timing as well as the amount of insulin, okay, are determined by a control law, by a control algorithm designed by experts. So the idea is that this is the input, okay? And by monitoring using sensor to monitor the glucose level of my body, I will dynamically, adaptively, automatically inject insulin into my body to control my glucose. Okay, wouldn't that be a much better alternative than this, right? Okay, so feedback control is not just for mechanical or electrical engineering system. It exists in everywhere, and including healthcare. Okay, I'm sorry. Okay, next time we'll change everything in English. Now, another way to classify control systems is based on their goal. There are 2 different basic goals. One is regulation, the other is tracking. For the point of regulation, the desired output is a concept. Okay, for example, the duty of the job of this person is to make sure that the water level of these tanks reach certain height. And once this requirement has been met, it will turn off the valve. Okay, pure and simple regulation. Who controls is a regulation problem, because For the base version, I just want to maintain the speed of my car at a predefined level. Now, for adaptive cruise controls, the problem is also regulation. But here, what I want to do is regulate the distance between my car and the car I want to follow. Okay, whatever I want to regulate. Okay, the set point is fixed, and here what we have is what we call a regulation problem. However, the desired output does not necessarily always be a constant. It can be a trajectory. For example, when you drive a car, say you have an autonomous vehicle, okay? You want a car to drive itself, but the road is not always straight, okay? It will go round and round and round, okay? So the trajectory the car has to follow is not a constant, okay? It's a trajectory changing with time, okay? So for this kind of problem, we call it trajectory tracking problems. For this course, the focus will be on regulation, okay? Why? Because it's much more fundamental, okay? But do not underestimate the importance of control regulation problem, okay? It is super important, and it is the basic building block for tackling the multiple control tracking problem, all right? All right, but you have to have an idea, okay? Set depends on set point is constant or not constant. Control system can be classified into regulation and tracking control systems. Now, again, I want to give you an example to show you that feedback exists everywhere. For example, this is our feedback system. Nowadays, many people use wearables like smartwatches. And so the sensor here is a smartwatch. It will collect my activities by using a gyroscope and accelerometer and sensor like that. And it will process the collected data using my mobile phone or using the firmware it has, okay? And it will output on my mobile phone screen to tell me how far have I run today? How much calorie has I burned today? Has I met my training goal today? Right? And as a person, our response, okay, to determine what my training schedule, including time of training, how much time I want to divide myself to training, okay, the intensity of my training, things like that. Now, this is also a feedback control. Typically, we call it biomedical feedback, okay? It is very important, okay? Let me put it this way, okay? Nowadays, many people in the world are overweight, and overweight can create all kinds of health-related problems. So control weight has become a universal issue in healthcare, right? How do you control your weight? Okay, people provide all kinds of solutions, okay? But apparently those solutions do not work for all people. So BMI, overweight remain a serious problem. One possibility is that if, let's say I'm a person with overweight problem, okay? One possibility, and it has been experimented, verified to be very effective, is when I wake up, the first thing I do is go to my scale to see how much I weigh. So I know exactly the weight of my body. And can I do it? And I can do this, let's say 3 times a day. When I see the reading on my scale just go higher and higher and higher, it generates a feedback action into my brain. And it will somehow still push me to control my diet. And this is also feedback, okay? I know where I am, therefore it becomes a command to push myself to make the right move, okay? Okay, another thing is that human body has many built-in feedback control mechanisms, okay? For example, circadian rhythm is a very, very important issue. It is so important that these three scholars, professors, won the 2017 Nobel Prize in Physiology and Medicine because their contributions on circadian rhythm. What is circadian rhythm? It means the function, the status of body has a period, and that period is 24 hours. So our body will change during different time of the day, okay? Our cortisol and melatonin is also has a 24-hour period, okay? So in this ways, our human body actually has a built-in controllers to track this trajectory, all right? And our glucose and our insulin also has a 24-hour period. And our blood pressure and our heart rate also has its own circadian rhythms. Okay, so this data show us that our body actually has many built-in control mechanisms, and they are dealing with tracking problems, all right? Okay, as I said, feedback control also means close to control, but there are more than, in addition to feedback control, there is another very important tool that we can use to improve the functionality of the control system, and that is feed-forward control, all right? Feedback control goes this way. You have an output, you measure it, and you can put it to your desired output, or what we call it reference, and then you generate an error. And with the error as the input of the feedback controller will generate a command to drive the plan. I will define the plan later, okay? Now, that's one control action. There is another control action. That is, you have the reference here. You feed forward, you send it to your feed forward controller, and it will generate another command to make sure that the output of the plan or the output of the system will match the desired input, all right? So what are the differences between feedback and feed-forward? Feed-forward controller acts proactively, okay, by computing control signal directly from the reference input, using a model or plan to anticipate the necessary action and achieve rapid response, okay? Because let's say, let me give you an example, okay? Let me finish this PowerPoint slide first. Simultaneously, the feedback controller acts reactively. So feed-forward, feedback reactively. This somehow, in some sense, is passive. This is, by contrast, active. Passive, active. Why is it passive? Because it's based on error. Okay, error is something given by the system. Okay, and so based on the output error, I have to passively do something about it. Okay, and feed-forward control is that I anticipate there will be some error. Okay, so let me do something in advance. Okay, to somehow counteract the factors that will cause the output error. Okay, let me give you an example. This is a real example, and you can find the video on YouTube. This is the multi-battery control method developed by Mercedes-Benz. Okay, it deals with the vibration problem of a vehicle. Okay, traditionally, when you sit in a vehicle, you want it to be comfortable. You don't want it to vibrate up and down all the time. Okay, now to do that, traditionally, what we need to do is design a very good suspension systems. So to diminish the disturbance caused by irregular road conditions or rough surfaces, okay? And that is classic. That is not feedback control, okay? Now, what Mercedes-Benz did for magic feedback, the magic battery control is that it has a built-in camera, okay? And with this camera, it will measure the road profile ahead of the vehicle using a sensor. And based on those road profiles, it will calculate the precise force needed to command the actuator, the suspension system, to move proactively. That is, it has built-in pump, okay? And after knowing the profile, and it knows this, let's say this pump will generate certain amount of ground reaction force to cause the car moving up and down. If I know what ground reaction force this pump will generate, why don't I just generate another force with the same magnitude but exactly opposite direction to cancel out this force caused by the pump? It can be done, and it has been done, okay? So this is what we call feed-forward control. As you can see, with feed-forward control, you can elevate the performance of the control system to another level because you anticipate what is coming. Instead of passively accept those coming disturbance and then do something about it, why don't I prepare beforehand? I do something beforehand, and whatever the disturbance is before it impacts my system, somehow I can do something to counteract this undesirable disturbance, the influence of this undesirable influence. All right? So the point I want to make here is that feedback is not the only option. Feed-forward control is another possibility. All right? Now, and you can see such a video of Mercedes-Benz multi-battery control on YouTube. Okay, and I encourage you to do that. Now, the basic idea of feed-forward control, as I said, is that you need to have a sensor to participate in the disturbance, and you use a feed-forward control to compensate or to counteract the influence of disturbance. All right. So if you can somehow these two factors, if they can cancel out one another, okay, then the system will not be influenced by the disturbance. Okay. Now, so okay, let's just skip this page because everything I have covered, everything in it I has already covered in our previous slide. Okay, now anything, the point I want to make in this particular slide is, again, I want to emphasize feedback is not the only option. Feed-forward is also very important. But for most of the control textbooks, the attention is on feedback, all right? The attention is on feedback, okay? Because because feed-forward Well, it's not complicated. Actually, it's relatively simple. Okay, but and if you know feedback, planning for feed-forward control is very natural and very straightforward. That I think is the reason why that the majority of the control textbooks, or all of the control textbooks, pay their attention mainly on feedback control. Okay. Now let's formally introduce the four fundamental elements of a control systems. Okay. Here in Chinese, I want you to learn these four building fundamental blocks of a control system. I want you to learn them by heart. Okay, memorize it. Okay, the first thing is you have a process to be controlled. And the next thing is you need to have an actuator which provide power to drive the process. If you have for example, for the ACC system, the process is, of course, the car. The actuator is the engine, right? Because with the engine, how do you drive the car? Engine provide the force, the power to move the car move forward, right? And then you need to have controller. Usually the controller is the human driver, and you need a sensor. Usually the sensor is the human perception system. You use your eyes, you use your hearing capability to understand the surrounding environment and then to determine what you will do with your car. Where you want to move it to. You want to decelerate, accelerate it, or maintain the same speed. Okay? So four fundamental blocks. Okay? Now, this together form a closed-loop feedback system. Now, this is a system because we have an input here, we have an output here, and these four elements together become a block. Okay, become a feedback control system. Here, the output is the actual output. What I mean actual output is the actual condition of the system to be controlled. And here the input, remember, is the desired output response. Like the air conditioner, you set a desired room temperature. And then the air conditioner within its built-in temperature sensors will measure the actual room temperature. And the actual room temperature will be compared to the desired room temperature. And then it comes out with a temperature error. And the controller within the air conditioner will decide what to do with its motor. Okay, will increase the speed of the motor or decrease the speed of its motor. Okay, now, and the process, of course, is the room where the air conditioner is in. All right. Now, the process itself can be a procedure or a real object. When I say real object, I mean something you can see with your eyes, something you can touch with your hands, such as a vehicle, such as a missile, such as an airplane. All right. When I say procedure or process, it means a phenomenon that you cannot see and touch. For example, room temperature control is a process. You don't see temperature. You don't touch temperature. Of course, you feel temperature. But temperature changing is a process. Okay, temperature itself is something you cannot personally, physically touch. You can feel it, but you cannot grab it. Okay, all right. Now, remember the input for control system. Input sometimes is also called the stimulus, and typically it is a desired response, desired output. All right, and the output sometimes is also referred to as response. and it is the actual response of the system that you are trying to control. Okay, let me go back to this diagram, which is very important. Remember that I want you to learn this diagram by heart. Now, I told you that this is a feedback control system because it has its input, it has its output. Now, with the same definition, these four fundamental building blocks of a feedback control system, each of them is also a system. Why? Because each of them has its own input, has its own output. So it's actually a arrangement of four subsystems, which are controller, actuator, process, and sensor. Okay, so you have these four subsystems, and together with such a feedback configuration arrangements, you come out with a feedback control system. How? Next, okay. Now this is about actuator. Okay, here it means it says that actuators provide this power source. Okay, now otherwise you will ask the question where the process input come from. It comes from the output of the actuator, and the controller send commands to the actuator, tell actuator what to do, just like driver tell the engine what to do. Okay, and to design a controller, okay, it divided into two parts. One is, of course, hardware, but our focus is on software. The software means that for a controller, we need to design or develop a control law for the feedback control system. And that is the central focus of this system, okay? But we will not jump in directly to tell you how to design a control law. That is not how it works, okay? Remember, what is the goal of control? Control is to make things behave like we want, okay? It can be a car, it can be the temperature of the room, but it also can be a person. Let's say my kids are all in their 30s. So, but when they were teenagers, I really want to control their behaviors. Okay, because they didn't know what to want. And they don't listen to me. They don't listen to their teachers. They didn't do well in school. Okay, their manners, to me, had serious problems. Okay, how do I control them? Okay, I punish them, I reward them. Okay, if they do poorly, I punish them. If they do good, I get them gifts. That's not how it works. Okay, people are not that simple. So the first thing I need to do is not come up with a strategy to how to control my teenager sons. The first thing I have to do is I have to understand them. What were they thinking? What did they want? Okay, what kind of problems would they suffer from? After understanding what's inside their brains, only after understanding what they were thinking can I come up with a strategy, effective strategy to control them. Okay, control, of course, in this sense, seems to imply a bad thing, but it is really not. Control them is that I want them to behave like a good young man. And I consider that the duty of a parent, all right? But the point is, I'm not saying you two have to agree with my way of education, of raising children. That is not the point here. The point is that understanding the system is very important. So we don't come out directly with a control strategy. How do you control the system? We will build the big fundamentals. Before you know how to come out or design and control strategy, we first have to have methods to help us understand the behavior of dynamic systems. only after understanding, we have deep understanding of the behavior of dynamic systems, we can come up with good, effective, efficient strategy for control law. Okay. Now, here is the definition for a term. Like I said, there are four fundamental blocks for feedback control system. Sometimes the actuator and process are lumped together. Okay. When they are lumped together to form an independent subsystem, we call such a subsystem plant. Okay. So next time when you run into the term plant, remember that it is actually the union of actuator and the process. Okay. And the actuator has to come ahead of the process. Okay. Now back to the control law. What is a control law? Control law is a mathematical relationship of algorithms that determine how a controller calculates its output signal based on the input information. And the input information, at least for this course, is output error of the feedback control systems. Okay. In mechanical engineering application, the controller specifies how measurements, that is, output provided by the sensors outputs are processed to generate control commands, and the command then sent to the actuator. I want this motor to generate how much torque. Okay. Now, for example, there is one very popular controller, which is called a PID controller. Now, what is a PID controller? It basically consists of three components. The first component is that the controller, the controller outputs of this part is proportional to the output error. Okay, the larger the output error, the more corrective action I will apply. Okay, that makes sense, right? Now, what is derivative control? In addition to the magnitude of output error, the changing rate of the output error also matters. Is the output error increasing or decreasing? If the output error is large, but it is decreasing, then is probably output error is not such a big deal because it is coming down. But if the output error is large and it is keep increasing, then I need to do more about it. So this part of the control action is proportional to the derivative of all the changing rate of the output error. And the final part, which is the third part of the control law, PID control law, is integral. That is, my control action for this part is not just based on the current status of the output error. I look back the history of the output error. Okay, output error sometimes is positive, sometimes is negative. Okay, I integrate them and to see its average past history profile. All right, so one is current condition, one is changing rate, and the other is the past history. When you put those three ingredients together, you come out with a PID control. And this is a very popular control law, okay? But I wouldn't say it is the solution to any problem. Okay. In my personal humble opinion, I think PID control, what it can do is relatively limited, all right? But nevertheless, it is a very good starting point. All right. So all right, I'm sorry. Let me check the time to make sure that, okay, shit. All right, let's take a 10 minutes break. 谢谢。